We continue with 11.5 after checking the alternating series. We will see now another tool that we can use. It's called Absolute Convergence. It can be used on alternating series in certain cases and on other series that have mixed signs, positive and negative. So we will see how it works. It's quite straightforward actually. So the definition here is you have a series and then you take absolute value of each term. So that means now every term of this new series is a positive number, right? So those absolute values here, so that's called now the series of absolute values. Okay, so nothing special. Now the definition is a series AN is absolutely convergent when the series of absolute values is convergent. So essentially we take, let's say, series of negative 1 to power n divided by n squared. And then we take absolute value, we'll get a series of 1 over n squared. So if the series 1 over n squared is convergent, then the series, the alternating version, is also convergent. That's what it means. And we will say that this series here, when it's convergent, then the original series is absolutely convergent. So it's not the series itself, it's about the series of absolute values. When the series of absolute values is convergent, we say that the original series is absolutely convergent. Now this is useful tool for alternating series and also for some series that have mixed signs that are sometimes positive, sometimes negative, but they are not really regular, they are not alternating. So very important thing is that when a series is absolutely convergent, then it is also convergent, meaning that since the series, for instance, 1 over n squared, we know that's a p series with p equal 2, so it is convergent. That means that the alternating version, so the series of minus 1 to power n divided by n squared, that's an alternating series, that series is also convergent since it is absolutely convergent. When the absolute value series is convergent, then the original series is also convergent. So that's very powerful. We will use this result in many cases. Now, since we have this absolute convergence, there is another type of convergence called conditional. That's when the series itself is convergent, but its absolute value version is not. For instance, we know that harmonic series is divergent, but we showed that alternating harmonic satisfies both conditions of alternating series and it's convergent. So the alternating harmonic is convergent, but its absolute value version is harmonic series. That one is divergent. So we will say that alternating harmonic is conditionally convergent. So it's not absolutely, it's just conditionally. So those are the notions essentially. We have absolute convergence, conditional convergence. So some series are absolutely convergent, others are only conditionally convergent, and we can do nothing about it. Now what is important is when the series is absolutely convergent, we know immediately that that series is convergent. Obviously series with positive terms, they are themselves series with absolute values, so it's the same thing. But for the alternating series or series with mixed signs, if we prove that the absolute version series is convergent, then we will know that this series is absolutely convergent. So the original series that is maybe alternating or mixed sign will be convergent as well. So this is very powerful. If we can prove that some series is absolutely convergent, we can prove that that series is automatically convergent itself. So sometimes we will use this tool of absolute convergence, because sometimes we just don't have any other choice. In other cases, the question will be, is this series conditionally convergent or absolutely convergent? So in that case, we will start with checking if the series with absolute values is convergent. If it is, we win. The series is absolutely convergent. So that's cool. So here, in this situation, we have an alternating series, and the question is this series absolutely convergent? Well, maybe, maybe not. How can we check? Well, we will check if the series of absolute values of these terms is convergent. So the terms are taken in absolute value, so the sign will be positive now, always plus, 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 plus. So we just lose the minus 1 to power k plus 1. So we will have a series with only positive terms. So that's why it's absolute values. And now we check if this series is convergent. In this situation, 1 over 2 to power k, we recognize that this is a geometric series. The term r is 1 over 2, so 0.5. It's smaller than 1 in absolute value. So this geometric series is convergent. This means that our alternating series here is absolutely convergent, which means it's also convergent itself. So you see, once you have absolute convergence, it means that the series itself is convergent and its absolute value version is also convergent. So that's very powerful. Here, for instance, we have another alternating series. So minus 1 to power n minus 1 divided by n squared. So let's see if this is absolutely convergent or not. So first thing is we take absolute value of the general term. So we'll get only the positive part. So the change in sign disappear. We only have plus, 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 plus everywhere. So now we remember that this is a p series with p equal 2. So it's convergent. This means that the absolute value version of the original series is convergent, therefore the series itself is absolutely convergent. That means that this series is also convergent. Okay, so obviously they converge to two different numbers, right? But both of them are convergent. Here we have an example of alternating harmonic, so 1 over k or 1 over n with a changing sign. We proved already that this is an alternating series. We checked the two conditions. The general term goes to 0. The next term is smaller than the current term. So both conditions are satisfied for alternating series test. So using alternating series test, we proved that this alternating harmonic series is convergent. Beautiful. Let's see if it is absolutely convergent. For that, we need to check what's happening with the series of absolute values. So again, we take absolute value of the general term, so the sign will be plus, plus, plus non-stop. So we will get our regular harmonic series. Well, we know already that this is a p series with p equal 1 and it's divergent. So that means that the absolute version series, so absolute value series, is a harmonic series and it is divergent. But the original series is alternating and it is convergent by alternating series test. So what we have now is that the alternating series is convergent, but the absolute value version is not. Therefore, this alternating series here is conditionally convergent. So it's not absolutely convergent because the series of absolute values is actually here harmonic and we know that one is divergent. So therefore this series here, alternating series, is only conditionally convergent. So it's not absolutely, it's only conditionally. So you will see that some series are absolutely convergent, which means the series of absolute values is convergent, therefore the original series is also convergent. And some series, only the alternating version is convergent, but the version of the series with absolute value is not, like in this case. So then we will say that the original series, the alternating one, is conditionally convergent. So this is just vocabulary that we need to remember. Now some series, like this one here, you have sine k divided by k cube. So sine k changes sign. Sometimes it's positive, sometimes it's negative. But it's not regular. It's not one term positive, one term negative, one positive, one term negative. It's not alternating. So this is a series with mixed signs. It's not alternating, so we cannot use the alternating series test. Oops, what do? Well, in this case, we have no choice. This is a mixed sign series. We have to use absolute convergence test. If we succeed to prove that absolute version is convergent, we win. If we don't, then we can do nothing about it. We cannot conclude anything. So in mixed sign series that are not alternating, our only tool for now is absolute convergence at this stage. So here we had sine k divided by k cube, so we take absolute value. K cube is obviously for k 1, 2, 3, 4, so it's positive. So sine k is smaller than 1, right? Absolute value of sine k goes between 0 and 1. So this is smaller than series 1 over k cube. So our absolute value series is smaller than the p series with p equal 3. Now we know that the p series with p equal 3 is convergent. So now we will use direct comparison test. Since this series is smaller than a convergent series, therefore this series here with absolute values is also convergent. What does it mean? Well, it means that our original series is absolutely convergent, therefore it is also convergent. So we remember that if a series is absolutely convergent, it is automatically convergent as well. So here we had to use the absolute value version series, and then we made a comparison with a p convergent p series. So now by direct comparison test we know that the series of absolute values is convergent, therefore the original series is convergent as well. So it's absolutely convergent. Another example with cosine. So cosine n divided by n squared. So we need to check if it's convergent or divergent. Again, this is a mixed term series. So some terms are positive, some terms are negative, but they are not regularly distributed. It's not one positive, one negative, one positive, one negative. It is a mix. So this is not an alternating series, so we cannot use alternating series test. At this stage, our only tool is to try the absolute convergence test. So again, we take the absolute value of the term. Now again, absolute value of cosine n is between 0 and 1. So we'll use this comparison here. So cosine n in absolute value is smaller than 1, so divided by n squared. So the series 1 over n squared is a convergent p series with p equal 2, we know that. So now by direct comparison test we can say that the series of absolute values here is also convergent by direct comparison. Therefore our original series is absolutely convergent, therefore it is convergent itself. So this is straightforward application. Now a curiosity here, we remember that when we have a finite sum, let's say 20 terms, we can add them in any order, we always get the same number, obviously. Now in some cases when we deal with the series, it's not always the same value. So if the series is absolutely convergent, we can change the order of terms, it doesn't affect the sum, so the sum will be the same. So if you have an alternating series that is absolutely convergent, you can mix terms as you like, you will get the same result. However, if your series is only conditionally convergent, then a rearrangement of the terms might lead you to a different sum. So that's fun, which means if a series is conditionally convergent, we need to add the terms in order that they appear. We cannot mix them. So that's very important. This is just an illustration. We remember that our alternating harmonic series is convergent. Later on we will see it's convergent to Ln2. And then we do some multiplication of the terms, and then we add them. So we multiply both sides by 1 over 2, so we'll get here this times 1 over 2, and then every term here multiplied by 1 over 2, so we get it here, and then we add them. So at the end what we get is the sum, so this plus this is this expression here, so right side plus right side is 3 over 2 ln 2. Now what we observe is that these two series, they have the same terms, but they are not in the same order. So 1, 1, minus 1 over 2, minus 1 over 2, 1 over 3, 1 over 3, minus 1 over 4, minus 1 over 4 here, 1 over 5, 1 over 7 is here, 1 over 6 would come here. So essentially all the terms are there, but they are not in the same order. And we see that if we order them as they appear, the sum is ln 2. However, if we mix a little bit, we get a different sum. And we remember that our alternating harmonic series is convergent, but it's not absolutely convergent. So that's something very interesting. This is just an observation. And actually there is a result that was proven that when you have a conditionally convergent series, you can take any real number that you can imagine, pi, radical 7, minus radical e, whatever you like. And there is a rearrangement of that conditionally convergent series whose sum is actually your number that you picked. So that's very powerful. So this is just a curiosity for us. So now I'll just go through a couple of examples. There are several examples here that are solved, over 30. So you can check them, but I'll just go quickly through a couple of them to make sure that we see some of these interesting cases. So here the question is always, is the series convergent or divergent? Sometimes the question could be, is the series absolutely convergent or conditionally convergent or divergent? So in that case you would try to start with absolute convergence. If you are lucky, then the series is absolutely convergent, and it means it's also convergent. If you're not lucky, well, maybe the series of absolute values is not convergent, then you go to the series, the alternating version, to see if that one is convergent using alternating series test. So here we have an alternating series, so this term here is responsible for the change of sign, and the general term is here. So now what we do is we need to check, since this is an alternating series, we will try to see if we can verify both conditions. So the first condition, we can pick one we like to verify, but the easiest one to start with is the limit of the general term. So is the limit of the general term 0? If it is, we move on. If it's not, we know immediately that by the divergence test, whenever the general term of a series is not going to 0, so its limit is not 0, series is automatically divergent. So that's something to test first, probably, because it will save us some work. So in this situation, we compute the limit of the general term. We find that is 3 over 2, so that's not 0. Therefore, by divergence test, we know that this series is divergent automatically. If we check a little bit, we could see that all the positive values converge to 3 over 2, and all the negative values converge to minus 3 over 2. So essentially, we would see that discrepancy, and that means that the limit does not exist. So that's an important thing to do. First thing is to check if the general term goes to 0. So we have a couple of examples with the same procedure where the general term actually is not going to 0, so the limit is not 0, therefore the series is divergent. So I just list a couple of them here. In this case, we have e to power 2 divided by n. So when n goes to infinity, the exponent goes to 0, so exponential 0 is 1. So the limit here is 1, it's not 0. Therefore, the general term is not converging to 0. Therefore, by divergence test, the series is divergent. So in the process of trying to check if the alternating series is convergent or divergent, when I start checking things, I always check first if the general term goes to 0, because that one, if it's not satisfied, means the series is divergent. If it is satisfied, I need to move on the next test. So this is another case with tan inverse. When n goes to infinity, tan inverse goes to pi over 2. So by divergence test, this is divergent because the general term doesn't go to 0. Here cosine pi over n, when n goes to infinity, pi over n goes to 0, so cosine 0 is 1. So the limit is 1, it's not 0, therefore by divergence test, the series is divergent. Here, again, we have an alternating series. The general term is 1 over e to power n. It's easy to see that when n goes to infinity, this term here goes to 0, so first condition is satisfied. And the second condition for the alternating series test is to check that bn plus 1 is smaller than bn, which is obvious. E to power n plus 1 is bigger than e to power n, so 1 over e to power n plus 1 is smaller than e to power n, so both conditions are satisfied, so that's easy to check. So we could easily see that this alternating series is convergent by alternating series test. Now a question could be, is this an absolutely convergent series? Well, let's check. So basically we take the absolute value of the general term, so we get 1 over e to power n as previously. Now we realize that this is a geometric series with r equal 1 over e, and that's smaller than 1, therefore the geometric series is convergent, which means that this series here of absolute values, which is a geometric convergent series, so it's convergent. That means that our original series here is absolutely convergent and therefore is convergent. So we can have two ways to prove that this is convergent by alternating series test. But if the question is this absolutely convergent, then we must use the series of absolute values. So in this situation, my procedure here is maybe an overkill, because I'm proving that this is absolutely convergent, but actually it's easier than checking the conditions for the alternating series also. So it's up to us, but sometimes the question will be, is the series conditionally convergent or absolutely convergent? Here we have sine n over 2 to power n. So this one here is not alternating, because sine n will change signs from positive to negative, but not regularly. So it's not an alternating series. So the only tool for now is this test for absolute convergence. We have no other. So we try. If we win, if we succeed, we win. So here we take absolute value of the general term. So sine is between 0 and 1. So this is smaller than 1 over 2n. Now the series of absolute value is smaller than the series of 1 over 2n, which is a geometric series with r equal 1 over 2, which is more than 1 in absolute value. So we know that the bigger series is geometric convergent. Therefore, the smaller series by direct comparison test is also convergent. Therefore, our original series is absolutely convergent. Therefore, it is convergent. Oof. Here, a similar example again. This series is not alternating. Again, it's our problem, so we cannot use alternating series test. We observe that the general term goes to 0. That's important. But now our only tool is the trial for absolute convergence. So in this case, we have 1 plus 2 to sine n upstairs. So sine goes from 0 to 1. So the maximum value for sine is 1. So here we have 2 times 1 as maximum value plus 1, so that's why we have 3 here. So it's 1 plus 2, 3. So we know that the series of absolute values is smaller than 3 divided by n cube. Now 1 over n cube is a convergent p series with p equal 3. Therefore, by comparison test, the series of absolute values is also convergent, which means that our original series is absolutely convergent, therefore it is convergent. So we remember, when the series is absolutely convergent, it is also convergent. That's valid for alternating series as well as the series that are not alternating, but they change sign. If the series is absolutely convergent, it is automatically convergent. This is just an example to see that sometimes the sign of the series could come as a very weird expression. So if we just try to list a couple of these values for different values of n, so when n is 0, when n is 1, so we just compute, we will see that the sign goes 1, minus 1, 1, minus 1, 1, minus 1. Therefore, actually, this sign expression upstairs is just the change of sign plus minus. So it's negative 1 to power n in this case. We start at 0 here. So this is an alternating series actually. So it was not obvious from the beginning, but if we check the value at different values of n, what is the value of sign of the expression, we realize it's 1 and minus 1. So this is just a small trick. So sometimes in these situations it is just an alternating series. So in this case we could use the alternating series test. The general term goes 2, 0, that's good, so one condition satisfied, and the other one is obviously with n plus 1, this will be smaller than just the expression with n, so both conditions are satisfied, so we can use the alternating series test to prove that this series is convergent. So that is kind of straightforward application of the alternating series test. Now it could be interesting to see if this series is absolutely convergent or conditionally convergent. So for now we know that by alternating series test this series is convergent, but we don't know if the absolute value version is convergent as well. So if we check what's happening with the absolute value version, we'll get an expression like this, and we need to now figure out if this is a convergent series or not. So using limit comparison test, so we need to do the details obviously. So the dominant term upstairs is 1, the dominant term downstairs is radical n. So we will use as comparison series 1 over radical n. We do the process for limit comparison test, and we will show that the limit of the ratio would be 1, and that means that this series and the series of 1 over radical n, they are both either convergent or divergent. And since we know that radical 1 over radical n is divergent p series with p equal 1 over 2, that means that this series here is divergent as well. In that situation, what we proved is that alternating series is convergent by alternating series test, but the series of absolute values is not convergent, is divergent. Therefore, our original series, this one here, is only conditionally convergent. So it's not absolutely convergent, it's only conditionally convergent, because the series of absolute values is divergent, unfortunately, by limit comparison test. So the work needs to be done here. Another example of the same process. So here, what is interesting is to check these conditions for alternating series. Sometimes it's not so obvious. So in some cases, we need to use the associated function. So these are the examples just to show you that in some situations like this, it's very difficult to figure out if this, for instance, the general term, it's easy to show that it is going to 0, but it's not so obvious to prove that the next one is smaller than the previous one, because you have n upstairs and downstairs, so it's not so obvious. So in this situation, we would use associated function and compute the derivative. If the derivative is negative, that means the function is decreasing. That means that our general term is decreasing, so that will satisfy the second condition. So the first derivative in this case is ugly, but what matters is just the sign. We need to figure out what's the sign. So downstairs everything is positive, and upstairs we see that the upstairs will be negative if x is bigger than 3 over 2, which is 1.5. So as soon as x is bigger than 1.5, this expression here is negative. That means the function is decreasing for x bigger than 1.5. That means for our situation, our terms will be decreasing for n greater than 2. So that's good. So the second condition for alternating series test is satisfied, and we can apply now alternating series test and use it to conclude that our alternating series here is convergent. However, if we would like to check if it is absolutely convergent, well, we need to see what's happening with the series of absolute values. Again, it's gonna be dirty, it's not clear. So in this situation, again, it's easier to use the limit comparison test. So dominant term upstairs is radical n, dominant term downstairs is 2n. So in all, it's the comparison series is 1 over 2 radical n. We do the work for limit comparison test. Here I skipped it, but we need to do the work properly. We will conclude that the condition for limit comparison test is satisfied, and then since we know that the series 1 over radical n is divergent P series, therefore this series here is divergent, so the series of absolute values is divergent, unfortunately, which means that our original series here, the alternating version, is only conditionally convergent. So that's how we use these results. Again, similar example, I'll skip it. So you see here the derivatives are a little bit ugly, so when we regroup, it's just important to see the sign. From which value of x is this expression negative? So in this case, when x is bigger than 2, the expression is negative. So for n bigger than 2, our terms in the series will be decreasing. So that's what we need also for the alternating series test. And again, if we want to see if it's absolutely or conditionally convergent, we check the absolute value series version. Here the dominant term is n squared, downstairs is n cubed, so all in all is 1 over n. We will use limit comparison test in all its beauty, and we will find that the condition is satisfied. So since the series 1 over n is harmonic divergent, the series of absolute value is divergent, therefore the original series is only conditionally convergent. So some of these cases are straightforward. Here, if I wanted to check if the series is absolutely convergent, I will need to see here if the series is convergent or divergent. We remember that ln is smaller than n, so 1 over n is smaller than 1 over ln, and we know that series of 1 over n is harmonic series which is divergent, and by direct comparison this series here would be divergent also. Therefore our original series, alternating series, is only conditionally convergent. Sometimes, this is just an example, we saw that we need to use associated function to find if the expression is decreasing. Sometimes you will need it to find if the limit of the expression is 0. So unfortunately here is not so obvious, so we use associated function with x positive obviously. So in this case we have infinity over infinity, so we use L'Hopital. Sometimes you use L'Hopital twice depending on the situation, and then we find that the limit here is 0, therefore the limit of our expression here will be 0, so the first condition is satisfied. And again, it's not obvious to see if the condition here is satisfied or not, so we need to use the first derivative. If the first derivative is negative, then this expression here is satisfied. But again, the computation might be ugly, so we just need to see when this derivative is negative for which values of x. So here, for x is bigger than 2, we just compute this number essentially. So for x is bigger than 2, this expression will be negative, so the function is decreasing, therefore the terms in our series will be decreasing. So that verifies the second condition. So in this situation, you see, to verify the conditions for an alternating series test, I had to use the associated function for both conditions. So sometimes it's only for one, sometimes it's for both. How do you know? Well, if it's not obvious to compute the limit, you need to go with associated function. If it's not obvious to see if the general term is decreasing with n, you need to go for the associated function. So those are essentially some examples. Here is another one, maybe a bit artificial, just to show you that sometimes you need to be creative. Obviously this is an extreme example where we have the series here that we proved by alternating series test that is convergent. Now if the question is it absolutely convergent or only conditionally? Well, we need to check the series of absolute values. That's a much more work. Here it is a bit more complicated because actually I need to figure out if this series is convergent or divergent. So I had to be creative in my comparison. So n is smaller than 1.5 to power n. So here the expression is n divided by 2 to power n. So I divide both sides by 2 to power n. So I get something like this, and then I have 3 over 4 to power n. This is a geometric series that is convergent with r smaller than 1. Therefore, by direct comparison, this series is also convergent. Therefore, we could conclude that our original alternating series is absolutely convergent. But again, this is more creative, requires more work. That's why I put it here just as an example to show you that sometimes you need to be creative in creating comparisons. Another example here, cosine n pi. It's a mystery, but if we just compute the values, we get positive, negative, positive, negative, positive, negative. So essentially cosine n pi is only changing the sign. So it's minus 1 to power n. So essentially this is an alternating series disguised in a complicated complicated expression, but it's only an alternating series. Now we need to see if it's absolutely convergent or not. Well, in this particular case we just proved it because we have it here. So those are some examples that you can see here. Again, to check, we have an alternating series. So to check the conditions, here it's not obvious, so we need to use associated function and then use L'Hopital to compute the limit and then compute the first derivative of this ugly expression here. Use the derivative. If the derivative is negative, then the function is decreasing, which means these general terms are decreasing, which satisfies the second condition. But again, the only important thing is to identify when the expression is negative. You will regularly have downstairs positive, and then your only goal is to see when the expression here is negative. And in this case, when n is bigger than 2 or when x is bigger than 2, it works. So that's pretty much it. You have plenty of examples here just to see a little bit different versions. So this one here is an alternating series. Now it's a little bit ugly. It reminds us of a telescoping series. So when we start checking the conditions, we need to see if this term here goes to 0 or not. If it does go to 0, we are happy. We move on. Now to do that, we use the associated function and the conjugate. So we need to be creative. And then we find that the limit is actually 0, so that satisfies the first condition. Okay, you could use the conjugate on this expression as well, it's not a big deal. Now to see if the expression is decreasing, it's more complicated. We need to use the first derivative and find when the first derivative is negative. Now here, again, it's a little bit easy because this term here is always smaller than this one, so this expression is always negative. So that satisfies the second condition. So by alternating series test, we know that this series will be convergent by alternating series test. Now if the question is this series absolutely convergent or conditionally? Well, we need to check what's happening with the series of absolute values, which is not obvious because this is now a telescoping series, so we need to write out the terms and then see the behavior of the nth partial sum. So this is the partial sum here. What happens when n goes to infinity? Well, we have radical n plus 1 minus 1, so this term here will increase forever. Minus 1 is not going to change much, so this means that the partial sum here is going to plus infinity, which means it's divergent. So the limit does not exist. Since the limit does not exist, it means that the general term does not go to 0. Since the general term does not go to 0 by divergence test, we know that this series will be divergent. Therefore, the series of absolute value is divergent. Conclusion: our original series is only conditionally convergent. So these are some more examples with hints. Again, when you have 1 over ln, you always try to compare it with 1 over n. So here we have alternating series. We check the two conditions straightforward, it's not a big deal. So this series is convergent. Now, is it absolutely convergent or conditionally? So we check the series of absolute values. We get 1 over ln. That series is bigger than series of 1 over n, which is harmonic divergent. So by direct comparison, this series of absolute values is divergent. Therefore, our original alternating series is only conditionally convergent. So those are some examples. You can check them on your own. It's not a big deal. It's always the same procedure. There is nothing particular. Pay attention when you have these cosines. They are a little bit confusing, but just try to evaluate a couple of them and then you realize it's actually just changing sign. I'm looking if there is any special case. So in some cases you'll need to use limit comparison test, not direct comparison test. This here, it's interesting because we have minus. It's not minus 1 to power something, it's just minus. So we can factor this minus outside. Okay, so it's not a big deal. We have this series here to check with the negative sign in front, so it's not a big deal. So this is not an alternating series, it's just a regular series, but everything is negative. Okay, so not a big deal. Now to see if this series is convergent or divergent, well, we have no much choice but to use limit comparison test with comparison for series 1 over n. So that's classical. Here, checking the conditions, the two conditions for alternating series test is straightforward, nothing special. In this case, we use a tool that we are skipping, so essentially you can ignore the second part because we are not doing anything with integral tests, so we can ignore the second part. But the first part, checking if the alternating series is convergent, it's straightforward to check the two conditions. So that's pretty much all we have. So take some time to just go through the slides and then try to solve quickly on your own the same problems. It's not difficult, just checking the conditions. And again, sometimes you will need to use associated function and compute the limit using L'Hopital eventually, or compute the first derivative to see if the function is decreasing, so if our general terms are decreasing. So some practice is needed, but this is in general easy material.